In this video, we're going to go through the calculations involved with iodometric titration to determine the oxygen content for our YBCO powder that we produced. So just a little bit of background on this before we get started. So the idea here is that we're using this type of titration to determine the copper valence because all the other metals have fixed valence, and that determination of valence tells us the oxygen content. So what we're trying to get out of this is what's the copper oxidation state and what's the oxygen content, because oxygen content will determine many of the superconducting properties. So that's what we're trying to get out of this. And so hopefully you've already watched the video on how this type of titration was determined and proceeded, but just very briefly, I've got the handout up here open. And so we ground into a fine powder, we weighed it out, we added potassium iodide, and then we dissolved with hydrochloric acid solution. This produced iodine, which is then titrated against with sodium thiosulfate, and we determine the volume of thiosulfate that we use. We have the mass, and from there we can calculate the oxygen content after we use the color indicator and so forth. So that's what we'll be working on this last portion of how do we calculate the actual properties in here. And so that's what this video will go over. And to do that, we're going to use some data from 2019. So you'll want to do this with your own data. This is just an example going over some of the 2019 data. So the first thing we're going to do is kind of collect up all of our data. So this is a sheet I have, again, going from spring 2019. So we're just going to take a couple samples and look at them and see how we calculate these quantities. So I've given you the normality of the thiosulfate used, the mass of the powder that we used, and then the volume before and after titration. This will all be in your spreadsheet that we provide you with all of your data for this semester. And so what I'm going to do is I'm going to go ahead and just go to my next sheet that I've kind of prepped, and I'm going to start entering that data. So the first thing is the mass. So let's look at sample 1 first. So we have 42.2 milligrams. So I'll go ahead and put that here, and we can get that. So we need, from the handout, the mass needs to be in grams. And so I have basically provided you with equations here, so make sure you use the proper units or the math won't work out. So essentially we need to divide by 1,000 to get mass in grams. And then the volume of thiosulfate we're going to take as the initial minus the final. And so if we go back, that's 8 milliliters. And then the normality was 0.03, so I'll also use that. All right, so those are all the quantities that we need. And if we sort of just bring up the handout really quick, the first thing that we need to do is to calculate 3x. And so 3x needs the volume, normality, molecular weight, and also the mass that you see here. So that's what we're going to do, and we're going to input that into a column, the cell right here. So let me just set this up. So on the top, we need the volume of thiosulfate, so that's this, and that is supposed to be in milliliters, multiplied by the normality, multiplied by the molecular weight. And so I've went ahead and taken the molecular weight of YBCO, and that's over here. And we're going to divide by 1,000 times the mass. And this, again, this is the mass in grams. All right, so this gives us 3x. And if we again, this is back from this equation that I gave here. So if you're going to use this equation, make sure you use the proper units that it says right here. All right, so from there, we want to calculate the oxygen content, which is 7 minus delta. So this is basically, if we go back all the way up to our equation, our formula for YBCO, it's the O part, right? It's basically telling us how much oxygen we have in this lattice. And so this is a rearrangement, basically, of the 10 plus the 3x term that we just calculated divided by 2. And if you're wondering where all this comes from, I've got the equations here on the last page of your handout. But let's go ahead and put this in, the 7 minus delta part into the equation. So that was, again, I'm just going to use a lot of parentheses here. So 10 plus the 3x, and then we're going to divide by 2. So this should be 7 minus delta. So what this is telling us right now is that there's the oxygen part. So if we, again, go back up here, so we have YBA 2 CU3 O, and then 6.87 is what that's telling us. So that tells us how much oxygen we have, and it's on the higher end of that scale, right? It's pretty close to 7. So that's generally good. High oxygen is good. All right, so that's not the end of the story, though, because if you can kind of think of this 7 minus delta is telling us how much oxygen content we have, right? Well, if we don't know how much oxygen we have, we can't determine an accurate molecular weight of the YBCO, right? Because we have to know how much YBA, CU, and O. So what that means is that this value was determined with a molecular weight of 658.13 grams per mole, right? But if we input this into the expression, we're going to potentially get something different. So if our molecular weight is different because of the amount of oxygen, then we need to account for that. And so what we're going to do is we're going to do an iteration. So we have the first value, and then we're going to plug this into the molecular weight formula, and then use that new molecular weight, and that's why you can see I've had multiple here. So I'm going to put this new molecular weight in here, and then we're going to go through the calculation, sort of go back to the start, calculate 3x again, 7 minus delta, and then put that new value, and so forth. So we iterate until we get a stable value. So let's go through that part. Calculate the molecular weight. So I'm going to start an equation here, and I'm going to start in order. So Y, and then BA, CU, O. So the first one is yttrium. So that's the weight of that is 88.90585. And so you can find these anywhere online in a textbook and so forth. And so you often don't need this many decimals, but I'm just gonna, that's what I got from my source. So so that's yttrium. And then there's 2 barium, so 2 times, and then the weight is 137.327, plus copper, there's 3 of them, so we're going to add, that's 63.546, and then the last part, plus, this is going to be the oxygen content multiplied by the 15.9994, which is for oxygen, right? So this will allow us to calculate the amount, or the molecular weight of YBCO with our current assumptions in here. So that's the new value. And so what we'll need to do now is we're going to take this expression here. So this only depended on the mass, the volume, and the normality, right? But this, we also have the molecular weight. So if we basically want to do that again, and instead of using the first molecular weight, we're going to use the second, right? So what I'm going to do for that is I'm going to fix the value of everything else other than the molecular weight. So that's K1. So everything else is going to be fixed. And I'm going to bring this down. So now if I click on this one, I'm using these same values, but I'm using the second molecular weight you can see here. then the same thing, this is just simply a function of 3x, so I can just extend this down. All right, so then, so this is my second round. So you can see the 3x got a little higher, and you can see that the 7 minus delta got slightly higher, but not much. And so here, if you, we're going to do the same process. We're going to see what effect that has on the molecular weight. And so if I extend this down, right, then it's using the second value now. And if I just keep doing that, I'll go all the way down here, right? So now the second value now uses this, and so forth. So I've just set it up to use each subsequent number that we've calculated. And what you see here is that the first one, it changed, and then it starts to stabilize, right? There's really no difference in these values down here. Same thing over here. This is what we really are interested in. And after the first one, right after, we got 6.87, and then we go to 6.89, you can round up to. And so you're getting the same thing. You're getting that stable after usually 2 or 3 iterations. And so I just did the extra ones to show you that it does stabilize, and you can see these last 3 are even just stable. So so basically, I like to report this to 3 decimals, or sorry, 2 decimals, 3 sig figs, and so that would mean that our value is 6.89, and that's kind of stabilized after the first recording. So that's how you kind of go through this. It's an iterative process where you have to calculate 3x based on an assumption in the molecular weight, and then you plug in your oxygen content that you get into the molecular weight formula over here and do the calculation again. And so you iterate until your oxygen content is in line with what to expect. And so that's where we're getting this value. So we're able to calculate the copper valence, which is a function of x, you can see in the handout, and then 7 minus delta, which is our oxygen content. And so just as a reference, if we want to see the variation in oxygen content, we can go back and look at the other sample 2, which was under an argon environment. And so the main difference is, let's kind of just, let me duplicate this. And I'm going to change this to 51.2. Double check that. Yeah, sorry, 51.6. And then the mass here, sorry about that. Let's just go ahead and do this again. So the mass, or sorry, the volume was the initial minus final. And so this, you can see it's a much lower volume, but everything else is the same. And so if we plug that in, we're using the same formulas, same thing here, we see that our new oxygen content here is 5.59. So you can see that compared to the oxygen environment, the oxygen content is much, much lower. And these are predicted to have lots of differences in terms of the properties between these two pellets. Because of the oxygen content, we can calculate with the iodometric titration. So this is how you go through and calculate those values.